Okay, so this is part 4. I accidentally hit stop instead of pause on part 3, so I had to upload it and start a new video. So anyway, ECG and lab values part 4. We are ready. Anyway, I'm not going to go through all that. So we're going to pick up where we ended off, which was, what is the rate? These are the 6 questions that you need to answer when you want to interpret a ECG strip. What is the rate? So we went over that. Heart rate determination can be done in one of 3 ways. Method 1 is number of RR intervals in 6 seconds, and we watched at the end of part 3, we watched the video of this lady down here telling how to do that in 6 seconds. 30 large squares equals 6 seconds. So you would have to make sure that you have a strip that has at least 30 large squares. And it's also good for irregular, like she said, it's good for determining irregular heartbeat. The method 2 is 300 divided by number of large boxes between QRS complexes. And the video before showed how you can do that for a regular heartbeat as well as an irregular heartbeat. For irregular heartbeats, you would have to do at least 3 QRS complexes. So R to R, R to R, R to R, and take 300 and times it by 3, and then divide it by your number of boxes. And if you want more detail on that, go ahead and look at part 3. This is part 4, believe that or not. So we already went through this on part 3. And so we are up to, where are we? What is the regularity? So let me go ahead and pause this. Okay, so I'm going to look at this video on rate and regularity rhythm.
Cardiogram, or ECG, or the Dutch or German version of the word EKG, is a tool used to visualize the electricity that flows through the heart. An ECG tracing specifically shows how the depolarization wave moves during each heartbeat, which is a wave of positive charge. And the way it looks depends on the set of electrodes you're using. This particular set of electrodes is called lead 2, for example, with one electrode on the right arm and the other on the left leg. So essentially when the wave's moving toward the left leg electrode, you get a positive deflection, like this big positive deflection corresponding to the wave moving down into the left and right ventricles. To read an ECG, there are a few key elements to keep in mind. One of them includes figuring out the rate and the rhythm. Now, there are a couple ways of figuring out the heart rate on an ECG. The first one is called the box method because you count the number of boxes between heartbeats. Each small box represents 0.04 seconds, and each big box is 5 small boxes. So each big box is 0.2 seconds. So to calculate the heart rate, you can count the number of small boxes between R waves since R waves are tall and pointy and easy to see on lead 2 of an ECG strip. You can find an R wave that has a peak that falls at the beginning of a box, and then count up how many boxes until the same point on the next R wave. So let's say that there are 4 big boxes and 1.5 small boxes between 2 R waves. Since you have 4 big boxes, that means 4 times 5 small boxes, plus that extra 1.5 small box, totals to 21.5 small boxes. And that means that there are 0.04 seconds times 21.5, or 0.86 seconds between heartbeats. So the units here are seconds per heartbeat. Now to get something a little more meaningful, we can take the inverse of that, which is 1 over 0.86 beats per second, or 1.16 beats per second. Now, since there are 60 seconds in a minute, we can multiply this by 60 and end up with 70 beats per minute, which is the heart rate. Now, if the distance between 2 R waves is exactly 1 box, then the heart rate would be 300 beats per minute, which is really fast. If R waves are 2 big boxes apart, or 0.4 seconds, then the heart rate is 150 beats per minute. 3 big boxes apart is 100 beats per minute. 4 big boxes is 75 beats per minute. 5 big boxes is 60 beats per minute. And finally, 6 big boxes apart is 50 beats per minute. Remembering these numbers makes it easier to make a rough estimate of the rate. For example, if there are between 3 and 4 big boxes between R waves, then we know that the heart rate must be between 75 and 100 beats per minute. Another method to figure out the heart rate is to count the number of beats in 10 seconds, which is the standard length of time in the rhythm strip portion of a 12-lead ECG. So in this case, we can count 15. Since this is a 10-second interval, all you have to do is multiply this by 6 to get the heart rate, which would be 90 beats per minute. The reason this little trick works is because you have 15 beats per 10 seconds. And again, to convert to per minute, you multiply by 60 seconds in a minute. Looking at this, we see that 60 divided by 10 equals 6 per minute. So 6 times 15 is 90 beats per minute. If the heart rate is too fast or too slow, it could be because something other than the SA node is pacing the heart. For example, there could be atrial flutter, which is when an ectopic focus in the atria, like an irritated atrial cell, starts to spontaneously fire between 250 and 350 depolarizations per minute, with only 1 out of every few atrial depolarizations passing through to the ventricles. To calculate the atrial rate, you can use the same methods as before, except you look at P waves instead of R waves. If one P wave starts on a heavy line, and the next P wave starts on the next heavy line, or 0.2 seconds later, then again you've got 1 beat for every 0.2 seconds. And multiplying by 60 seconds in a minute, you get 300 beats per minute. You could also remember that nifty trick where 1 big box is equal to 300 beats per minute. Another situation is atrial fibrillation, which is when there are multiple ectopic foci in the atria that start firing all at once. The atrial rate here can increase to 350 to 450 beats per minute. In this situation, only the occasional firing of an ectopic focus that happens to be near the AV node is able to make it through and down to the ventricles. In this case, the ectopic foci fired too quickly for the atria to be fully depolarized by any one of them. So there are few, if any, actual P waves. Without P waves, there's not a reliable method of determining the atrial rate just by looking at an ECG strip. And the heart rate's really just an estimate, because at this point the heart's just sort of quivering. Normally on an ECG, one waveform with its P wave, QRS complex, and T wave looks just like the next one, almost like they were just copied and pasted one right after another. And that's how a regular rhythm looks. An irregular rhythm, on the other hand, is when there's any change in the appearance, sequence, or timing of those waves. To help identify an irregular rhythm, you could look to see if every part of the waveform looks exactly the same, which would include the P wave, the QRS complex, and the T wave. If not, it could mean that there's an ectopic beat, meaning that it might have originated from an abnormal spot in the atria or ventricles. For example, this first P wave is deflected upwards, and the second is deflected downwards, which would indicate that it's an ectopic beat. Alternatively, an odd-looking waveform might have originated from the normal spot, which is the SA node, but then gotten thrown off course, which is what happens when there's a block someplace. In this example, there's a bundle branch block, which is where the signal can't go down one or both of the bundle branches, and this usually results in these wide QRS complexes. Next, you could check for changes in the sequence of the waves, most often involving the two depolarization waves, the P wave and the QRS complex. You can look to make sure that there's a P wave before every QRS complex, as well as a QRS complex after every P wave. For example, if there's a premature ventricular contraction like this, then there might be a QRS complex without a preceding P wave. On the flip side though, if there's a third-degree AV block, then there might be a P wave that's not followed by a QRS complex. All right, as a quick recap, one quick way to estimate the heart rate on an ECG is to remember that one big box is 300 beats per minute, two big boxes is 150 beats per minute, three big boxes is 100 beats per minute, four big boxes is 75 beats per minute, five big boxes is 60 beats per minute, and six big boxes is 50 beats per minute. To help identify an irregular rhythm, you can look at the morphology or shape of the waveform, and make sure that there's a P wave before every QRS complex, as well as a QRS complex after every P wave.
Ooh, I like it. All right.
Did you know it takes the average small business owner 2 years to make a software project?
Okay, so second question is, what is the regularity? And watch the video, and it will rate in regularity, a regular rhythm, and irregular rhythm. When you're looking for an irregular rhythm, you're looking for, does every part look the same? Does the P wave, is there a P wave? Is there a QRS complex? Is there a T wave? So with a premature ventricular contraction right here, there's no P wave before the QRS. There's a P wave, QRS, and then no P wave. So that was a premature ventricular contraction. And then the third degree heart block, no QRS after the P wave here. And then a PVC again over here. We already got that. Probably delete this, that's redundant. And then a wide QRS with a bundle branch block. I'm sure we'll be going over that a little bit more detail. And then, to sum it all up, he re-mentioned that one box is 300 beats per minute, two boxes is 150, three boxes is 100, 4 is 75, 5 is 60, and 6 is 50. And then with irregular rhythms, you're looking for no P wave and no QRS wave, to sum it all up. Okay, so now we are at question number 3. Narrow or wide QRS complex. So let's see what the EKG guy has to say about this.
In this lecture, we will discuss the QRS complex duration, or width, and things to consider when we see a wide QRS complex. We will end with some practice EKGs. In a previous lecture, we mentioned that there are 6 main things to look at when you are looking at the QRS complex on the EKG. We said the first was the amplitude, right, or the height of the QRS complex. The next was the duration, right, so how long, what is that time period, or the width of the QRS complex. The morphology, what does the QRS complex look like? So you can see this QRS complex here is different from one here, right? And this has a Q wave where there's one missing here, okay? So the morphology of the QRS complex. The next was the Q waves. Are there any Q waves present? So that one that we pointed out here. Are they significant or not? The axis along the frontal plane, and then the transition zone. Our focus in this lecture would be the QRS width, or the duration of the QRS complex. So this here, okay? When measuring the duration or width of the QRS complex, you want to measure it from the onset of the first deflection after the PR interval to the end of the QRS complex. So remember, we have our P wave, then our QRS complex, right? And the PR interval ends right here. So this is the PR interval. So we are measuring from the beginning of this point, right, to the end of the QRS complex. So notice where the calipers are placed at the beginning of the QRS to the end of it here, okay? So normally this should measure between 60 and 120 milliseconds, okay? That's 1.5 to 3 small boxes. Therefore, if it is greater than or equal to 120 milliseconds or 3 small boxes, it's considered abnormal, okay? So again, between 60 and 120 milliseconds is considered normal. Okay, so less than 120 milliseconds, and we know this is 3 small boxes wide. Okay. If you take a look at the two complexes measured here, you can see that complex A, which is this one here, is a normal complex of about 110 milliseconds. Okay, so that complex there is about 110 milliseconds, less than 120 milliseconds, so it's normal. Whereas if we look here at complex B, right, this actually represents a PVC. Okay, and that's a premature ventricular contraction. And as we can see here, that QRS complex is wide. So that width of the QRS complex is wide. Remember, this is a T wave. That's not our, this is our QRS complex. And we can see that PVC is wide, right? And it's measuring about 150 milliseconds, which is greater than 120 milliseconds. So we consider that a wide QRS complex. And that makes sense. It's a premature ventricular contraction, and meaning the ventricles are firing and they're going through their own cell-to-cell depolarization, which is a slower process than the normal conduction pathway. It's important to always measure the widest QRS complex in the EKG. There are some sections of the complex that are isoelectric and won't show up on the EKG. If you pick any lead, you may get a QRS duration that is shorter than is really present. And as you would expect, this could lead to serious mistakes in your interpretation. Therefore, make sure to measure the widest QRS complex on the EKG. Now, you probably have noticed this if you've looked at EKGs. Not all of them are easy to interpret. In fact, there are many cases in which there is an elevation and blurring of the beginning of the QRS complex or the J point, which is the end of it. In such cases, you need to be creative. Check the surrounding leads for more defined QRS onset or J point. You can then follow a vertical line from that point to the lead that you're trying to measure the correct interval. If you can't do that, then you may honestly need to just make a good guess. And if you need to make a guess, always assume the worst diagnosis. It's better for the patient if you overanalyze and assume the worst rather than underanalyze and miss a serious diagnosis. Okay, so what we're saying here is that if you can't make out an EK, whatever the complex is, say it's a different shape, look above and below it because those are happening at the same points. Okay, make sure to look at all the leads, as we said, and take the widest duration. So we mentioned that the normal QRS duration or width should be between 60 and 120 milliseconds. Or so that's 1.5 to 3 of the small boxes. All right, so that's our normal width of it. If it is greater than 120 milliseconds, or if it's even equal to 120 milliseconds, that's considered abnormal. Okay, so anything greater or equal to 120 milliseconds equals abnormal. Okay, and there are no limitations or exceptions to this rule, but there are some things that you should be thinking through when you see a wide QRS. Now take a look at the image we have here on the right. This is a list of the differential diagnoses for a widened or prolonged QRS complex in decreasing order of mortality. So the more serious ones are at the top of the list. So again, differential diagnosis for a wide QRS, we're saying it's greater or equal to 120 milliseconds in width. Okay, these are the worst ones at the top. All right, so let's go through these. Hyperkalemia can present with a wide QRS over time, right? And that can be actually fatal. That's at the highest, so this is the most severe. Another one is VTAC, or ventricular tachycardia. We can also see wide QRS complexes with idioventricular rhythms, including heart blocks, right? Also drug effects, overdoses, especially tricyclics, can cause it. WPW syndrome, which is Wolff-Parkinson-White syndrome, can cause wide QRS complexes. Remember, with that delta wave can make the width of the QRS appear wider. There's also the bundled branch blocks and intraventricular conduction delays that can cause a wide QRS complex. Premature ventricular contraction can cause wide QRS complex, as we saw here. Remember, we saw how wide that is. And there's also aberrantly conducted complexes. These are the least severe of these, and they can also cause a wide QRS. So whenever you see a wide QRS complex, I want you to start going through this list, okay, and try to identify what's going on. Remember, the most severe, rule those ones out first. Now, a way to simplify that list that we just discussed is by thinking of three main things when you see a wide QRS. Remember, wide QRS greater than or equal to 120 milliseconds, okay, in that duration. And the three I want you to consider are right bundle branch block, left bundle branch block, and intraventricular conduction delay. Okay, so remember, greater than or equal to 120 milliseconds. If it's less than that, remember it's normal. Okay, and again, we're looking at the QRS interval, the width of it, or duration. Now, those are really the three main things I want you to know, these three: left bundle branch block, right bundle branch block, and intraventricular conduction delay. Okay, and pretty much this whole list here falls into these three categories, and the only exception is WPW syndrome. Right, that's one that doesn't fall into these. So I want you to just keep this as like a side note, WPW syndrome. Okay, remember to consider that one as well. So all beats of ventricular origin have either a left or right bundle configuration. And hyperkalemia and drug effects are examples of intraventricular conduction delays. Okay, so we can write this here: hyperkalemia as well as intraventricular conduction delays. So as we said, that WPW syndrome also can cause a QRS that's widened, right? And this occurs because of the abnormal conduction of the impulse through that bundle of Kent. Okay, remember that accessory pathway that goes on, okay? And that stands by itself. It readily is identified by that characteristic delta wave in the short PR interval. Remember, in WPW syndrome, we can see that delta wave as well as the short PR interval. Okay, remember the delta wave. If this is our QRS complex, it's that beginning portion, okay? So it makes it appear that it's wider because it's coming earlier, and that's a result of the accessory pathway in WPW syndrome. Okay, so when you have a QRS complex that is greater than 120 milliseconds or even equal to it, think of the three possibilities if you've ruled out WPW syndrome. Those are right bundle branch block, left bundle branch block, and intraventricular conduction delay, which can be a result of hyperkalemia or a result of, this was the drug effects that we can see. Let's try some practice now. We will start with this EKG. Pause the video and take a few minutes to examine it. Focus on the QRS complexes, specifically looking at the QRS duration, or the width of it, and some of the causes that we just discussed. Restart the video when you're ready and we'll go over it together. So what we see here is called idioventricular rhythm. And we'll go over why that's the case in a minute. Now, on first glance, I'm sure you could see that there are wide QRSs, right, that are greater or equal to 120 milliseconds in width, or at least the three small boxes. Okay, so far we have wide QRS complexes. Well, what's our rate here? Well, we know to determine the rate, we can look either at the thick lines or we can get an approximate by knowing the duration of the EKGs, 10 seconds. And if we multiply that by 6, we get 60 seconds, which we know is 1 minute. So if we can count the number of QRS complexes going across the EKG and multiply that by 6, then we can get an approximate of the rate here. Okay, so let's do that. We have 1, 2, 3, 4, 5, 6, 7, and maybe 8 here. That's cut off in the rhythm strip down below. But okay, let's just say we have 7 times 6, which is a rate of 42 beats per minute. So our rate's somewhere, we'll say, in the 40s. Okay, that's our rate. And the next thing is, do we see any P waves here? Well, there aren't any in any of the leads. So we have a slow rate, right, less than 60 in the 40s here, and no atrial activity because we see no P waves. So this is likely from a ventricular escape beat of some sort. Remember, when the ventricle acts as a pacemaker, the rate is usually around 35 beats per minute. Right? We know the intrinsic rate of the ventricles is usually between 20 and 40, and usually the rate's around 35. So this is an idioventricular rhythm. And this is a rhythm you don't want to try to suppress with lidocaine or any antiarrhythmic drugs, because doing so you can actually precipitate asystole. Now, what do you think about the wide QRS complexes here? What do you think that the cause of it? Remember, we just went through that list. Well, let's go through some of them. Now, do we have left bundle branch block here? Well, if you look at leads V1 and V6, you can see, so here's lead 1 and V6 is here. You can see those S waves, right? And the S waves make this less likely that we don't have left bundle branch block pattern here. Now, how about the right bundle branch block? Well, if you look at lead V1, right, usually you'll see those rabbit ears, as you'll see the RSR prime pattern, but there's actually a negative QS here, right? So this is our negative QS wave, okay? So if you go through the list by the process of elimination, you'll see that this is an intraventricular conduction delay, or IVCD, okay? And we said that the most life-threatening cause of intraventricular conduction delay was hyperkalemia. Okay, and this is exactly what this patient's EKG shows, and the patient's potassium level was actually 8.7 milliequivalents per liter, so it's quite high. So the reason for this patient's EKG was hyperkalemia, and this requires immediate treatment. So remember, we look at, if we see wide QRS complexes, we rule out WPW. We don't see any delta waves, right, or short PR intervals. We don't even see a P waves here. So the next thing we look at are the right bundle branch block, the left bundle branch block, and if those patterns aren't met, we likely have an intraventricular conduction delay. Okay, and that's what we have here. That was the result of hyperkalemia. Okay. Let's try another EKG. Pause the video and take a few minutes to examine it. Again, focus on the QRS complexes, specifically looking at the QRS width and some of the causes that we discussed for it. Restart the video when you're ready and we'll go over it together. Well, on first glance of this EKG, you can tell that, again, we have these wide QRS complexes, right? They're greater than or equal to 120 milliseconds, which is 3 small boxes. In addition, it seems that there's an RSR prime pattern in lead V1. All right, and this is indicative of right bundle branch block. Remember, a wide QRS and then the RSR prime pattern is indicative of right bundle branch block. So here's RS and R prime. So we call that an RSR prime pattern, plus the wide QRS gives us evidence of that. Okay, so how about the ST elevation in leads 3 and AVF? Here's 3 and AVF. And there's some ST elevation in those leads. Do you think this is consistent with an inferior wall MI? Well, let's take a look at the whole EKG. Okay, so if you determine the width of the QRS complexes in leads AVL and V1, so if you look at AVL and V1, right, you'd see that the width of those is about 140 milliseconds. So if you then took that width and transferred it to the beginning of the QRS complex in leads 3 and AVF, so pretty much taking this width in each of them and transferring it onto here with your calipers, you would see that these were actually the same in width, okay? And in other words, the ST segment that we actually see here is a part of that QRS complex, okay? And the ST elevation that we see in 3 and AVF is not ST elevation, but rather the QRS complexes, okay? So what we're saying here is if you took the width of the QRS complexes in those leads, right, and put that on top of these ones with your calipers, you would see that these ST segments are actually not, it's not ST elevation, but rather part of the QRS complex. So we don't see ST elevation here. So is there any evidence of ischemia on this EKG? Well, do you remember the rules of concordance and discordance associated with right bundle branch block? The last portion of the QRS complex and the T wave should be opposite to each other in a normal complex, and this is called discordance. Discordance is the normal state in a bundle branch block. However, concordance is abnormal and if present in a regional distribution could indicate ischemia. Well, if you look at leads V2 and V3, you can see that they are concordant, okay? So leads V2 and V3. Notice that the last part of the QRS complex, this here, right, is going in the same direction as our T wave here, okay? And we call that concordance. All right? And remember, we said discordance is the normal state, so we don't have that normal state here in the bundle branch block. So seeing concordance in these leads with the presence of a right bundle branch block is consistent with ischemia. Now, an old EKG and clinical correlation are necessary to make the clinical decision for treatment. But as you can see here, the right bundle branch block pattern with concordance in these two leads may be evidence of ischemia. Remember, discordance is the normal thing you should see when you see this right bundle branch block or any bundle branch block pattern. Now, a few last things to point out in this EKG is that there's PR prolongation. Okay, so if you look at the rhythm strip down here, our PR interval is this. So remember, we have our P wave and then our QRS complex. The PR interval is from the beginning of the P wave up to the beginning of the QRS complex, and it should be between 120 and 200 milliseconds. Okay, so that is less than 5 small boxes. Okay, and as you can see here, it is actually prolonged. A little difficult to see, but this is a prolonged PR interval. And there's also evidence of intraatrial conduction delay, or IACD. When this could be due to left atrial enlargement or any problem in the atrium. All right, in the case here is left atrial enlargement, and you can see that if you can see like the M-shaped P waves in leads 2. All right, so here's lead 2, and if you can see here, they're a little difficult to make out, but these are M-shaped P waves. Okay, and then if you look at the lead V1, so lead V1, and you can see biphasic P waves. So look here. Okay, these are biphasic P waves, and that first part of the biphasic P wave, remember, it represents the, if we look here, this is the right atrium of the P wave, and this represents the left atrium. And we can see that first portion of it, this here, is actually greater than the first portion of the P wave in V6. So V6, you can barely make out the P waves. Okay, so remember the P wave in V6, the beginning portion is the right atrium, the end is also the left atrium, right? And we can see the beginning portion of that in lead V1 is greater than that in lead V6, okay? So this height here. All right, so let's move on to another EKG. Let's try this last one. Pause the video and take a few minutes to examine it. Again, focus on the QRS complexes, specifically looking at the QRS width and some of the causes that we've discussed for it. Restart the video when you're ready and we'll go over it together. Well, on first glance at this EKG, it appears quite scary, and it certainly is. The EKG was obtained from a patient that was awake and talking, however, 1 minute later ended up in cardiac arrest. So as you can see here, the QRS complexes are clearly greater than 120 milliseconds wide, and the rate appears fast. Okay, so we can see wide QRS complexes. Okay, and now let's look at our rate. Remember our rate, we know the whole width of this represents 10 seconds times 6 gives us 60 seconds, which is 1 minute. So if we count the number of complexes in that bottom strip and multiply it by 6, we can get an approximate rate. So let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and about 18. Okay, and then if we do 18 times 6, that equals 108. beats per minute. So we have a fast rate here, a wide complex of the QRSs. So we call this a wide complex tachycardia. Okay, and whenever you have a wide complex tachycardia, you should treat it as you would ventricular tachycardia or VTAC until proven otherwise. And make sure to look out for hyperkalemia, because actually this patient's wide complex tachycardia was a result of hyperkalemia. The potassium level in this patient was actually 9.7 or 9.7, so quite high, right? So hyperkalemia is the cause of this patient's wide complex tachycardia, and this needs to be treated immediately, okay, before the patient goes into asystole and ends up dying. Okay, so make sure you treat this, any wide complex tachycardia, just as you would with VTAC until you found another reason for the cause of this. Well, that's the end of this lecture. We discussed the QRS complex duration, or the width, and things to consider when you see a wide QRS complex. Remember that algorithm we discussed. We then ended with some practice EKGs. I hope you learned something.
In my previous videos, we talked about how to measure the PR interval. We talked about how to measure the heart rate on an EKG strip using the 6-second rule. And we also talked about how to interpret different types of EKGs. So after you watch this video, be sure to check out those other videos as well. So today I'm going to go over a quick tutorial and show you how to measure the QRS complex. But first, let's lay the foundation and talk a little bit about the QRS complex. So what does the QRS complex represent? The QRS complex shows ventricular contraction. This is when your ventricles are contracting, and on the EKG monitor, it's showing up as a big spike on the EKG strip, which is the electrical conduction system of your heart. A normal QRS complex measures between 0.06 to 0.12 seconds. This will calculate out to be 1.5 to 3 small boxes on your EKG strip. Now, when you're looking at an EKG strip, you have your EKG, and then behind it in the background are little small boxes. And those little small boxes represent a measurement of time. Each little small box represents 0.04 seconds of time. And you want to measure for a QRS complex 1.5 to 3 of those for it to be normal. And to measure that, you will start at the end of the PR interval to the end of the S wave. So let's look and see what a PQRS looks like. Here is one that I've drawn that is blown up so you can see it easier. You have your P wave, which represents atrial contraction. Then you have your QRS complex. This is what we're looking at today. This is our ventricular depolarization. Depolarization is just a fancy word for contraction. And we're measuring how wide or how narrow this is. And a lot of tachycardias, except for VTAC, you will have a narrow complex. But in VTAC, if you look at your QRS complex, it's really wide. And then you have your T wave and sometimes a U wave. So here in a second, I'm going to show you a blown up version of an EKG strip, and we're going to actually together measure out a QRS complex so you'll be familiar with it. Okay, so let's practice measuring a QRS complex. Behind me, I have drawn a blown up version of what an EKG strip would look like. On the EKG strip, like I said at the beginning of the video, you have the EKG, and then behind it, you have little squares. And so to make it easier for you to see on camera, I've blown it up. So behind me, these squares right here represent small squares, because that's what we're looking for when we're measuring the QRS complex. So each small square represents 0.04 seconds. And for a QRS complex, remember, you need 1.5 to 3 of those in order to equal the right measurement for a QRS complex. So let's look at our EKG strip. We have the P wave, the QRS complex, and the T wave, and sometimes a person has a U wave. So to do this, we start measuring at the end of the PR interval to the end of the S wave. So we're going to start measuring right here because that's the end of the PR interval. And then we're going to measure all the way to the end of the S wave, which is right here of the QRS complex. And then you're going to count how many boxes appear in between those. And right here, we have 1, 2. We have 2 boxes. And like I said, each box represents 0.04. So 0.04 times 2 is 0.08. So that is the measurement of our QRS complex. Now, sometimes these QRS complexes can be a little tricky, especially when you're looking on your EKG strip and those squares are really small. Sometimes the QRS complex will appear in half of a box. So one of the QRS complex may be measuring in half of this side of the box and then the other half of the side of the box. So half a half equals one side of a box. So you really have to pay attention and look and see where it's presenting at. But remember, a normal QRS complex measures 1.5 to 3 boxes, which equals 0.06 to 0.12 seconds in length. That's how you measure the QRS complex. I hope that helped you out, and be sure to check out my other teaching tutorials on the EKG strips and EKG rhythms. And please subscribe to our YouTube channel, and be sure to visit my website, registerednursern.com. Thank you and have a great day.
Okay, so we just went from a very stop. We went from a very up here video to a very low down here video. Complex is simple. That was very simple. Anyway, let's pause. Okay, let's look at this video. I know it's going to be some redundancy, but repetition is the key to learning.
Quick overview of interpreting EKGs. I'm going to share with you a quick 5-step method to help you be able to interpret any EKG without any problems. And following these 5 steps in the order that I give them to you will help you be able to interpret any normal EKG and any abnormalities with and be able to find and discover arrhythmias. So first of all, we need to talk about let's see here. Here we go. So first of all, we need to talk about normal conduction through the heart. With any conduction, with any heartbeat, the conduction should start within the SA node. Now the SA node sits in the top of the right atria, and the SA node should initiate impulses. Now from the right atria, that impulse should follow one of 3 pathways, all heading to the AV node, the atrioventricular node. And the AV node, as it's titled, it's the atrioventricular node, so it should sit, well it does sit, right between the atria and the ventricles. So the impulse is going to travel from the AV node, or the SA node, down to the AV node, which sits right between the atria and the ventricles, and from there it's going to travel down the bundle of His and into the Purkinje fibers. And these Purkinje fibers are going to initiate ventricular squeeze. So you have a few more ventricular fibers over here on the left ventricle. The left ventricle has thicker muscle, and it's actually pushing the blood out into the body, whereas the right ventricle is just pushing blood into the lungs. So you need a little bit more contraction power, a little bit more squeeze over here on the left. So for that reason, you're going to have a few more Purkinje fibers over there. So for it to be a normal rhythm, your electrical impulse has to initiate in the SA node, travel to the AV node. It's going to pause there for a second, and then it's going to travel down the bundle of His and into the Purkinje fibers. So that's what has to happen in order for this to be a normal EKG. Alright, so just as we talked about, the route of conduction for any normal EKG is going to start in the SA node, travel to the AV node, into the bundle of His, and down to the Purkinje fibers. Now, our heart is pretty unique in the fact that it has a couple systems set up that if our SA node fails, there's a couple fallback systems to ensure that we're still getting the blood, the oxygen that we need throughout our body. So as we talked about first in the SA node, that is going to initiate a heart beat, an impulse every about 60 to 100 times every minute. So that's why we essentially say that you know, a normal heartbeat is between 60 and 100 beats per minute. Now, if you're more athletic, if you have stronger heart muscle, that might be a little bit lower, and so we need to really examine our EKG to determine if the bradycardia is coming from athletic conditioning, sleeping, or if it has to do with you know, the impulse not initiating in the SA node. So your SA node is going to be your ideal pacemaker for your heart. It's going to initiate an impulse every 60 to 100 beats per minute. Next, so if there's a problem with your SA node, your AV node is going to kick in, and it's going to become the primary pacemaker of the heart. And it can initiate an impulse every 40 to 60 beats per minute. So if SA node fails, AV node is going to take over. And last-ditch effort, if your AV node fails, your Purkinje fibers, you know, the Purkinje fibers that come off the bundle of his, they can actually initiate an impulse every 20 to 40 times per minute. Okay, so we have our SA node, that's our primary pacemaker. It can fail. If it fails, our AV node is going to take over, and it's going to beat 40 to 60 times per minute. If that fails, then our Purkinje fibers can actually initiate impulses and cause ventricular squeeze 20 to 40 times per minute. So that's kind of why we want to look at our heart rate to determine where our impulse might be coming from. Okay, so let's look at a normal rhythm here, and let's determine what we have. So the normal rhythm, along our horizontal axis, we are evaluating time. So this is time passing. Along our vertical axis, we're evaluating voltage. Okay. So as our strip moves right to left, we're looking at time passing. And as our impulses move up and down, we're evaluating the voltage. Okay. So our normal strip, we're going to see our P wave, our Q wave, R, S, and T. Now this is just a basic introduction. There are different waves, there are different segments and things that we're not going to talk about. What we're going to talk about are the ones that you need to know in order to interpret your basic rhythms. So we have our P, Q, R, S, and T waves. Okay. Now we also have our QRS complex. Okay. Our QRS complex. We also have our PR interval. Okay, PR interval. And that's really kind of what we're going to evaluate. We're going to evaluate our P waves, our QRS complex, our PR interval, and we're going to evaluate our P to QRS ratio. Okay? So P wave, what is a P wave? Our P wave is going to signify atrial depolarization. Let's actually go here. So our P wave is going to represent atrial depolarization. Your P wave should be upright, it should be round, and there should be one P wave before each QRS. Okay? Our QRS complex, okay, so we have our P wave, atrial depolarization, QRS complex. That's going to represent ventricular depolarization. It should be upward. It should be, so this QRS complex is this space right here. It should be between 0.06 to 0.12 seconds. And on our actual rhythm strip, that's going to look like 1.5 to 3 small boxes. Okay, and it should appear just after your P wave. Okay, so you should have P wave, QRS, and then of course your T wave, which is going to represent your ventricular depolarization. Okay, and then we have our PR interval. And the PR interval measures from the beginning of the P wave to the beginning of the R wave. Okay, and what that's going to represent is that's going to represent the onset of atrial depolarization to the onset of ventricular depolarization. And essentially what that's going to tell us is it's going to tell us how long our impulse is being held in the AV node. So what the AV node does is it takes our impulse from the SA node and it holds it just for a second in the AV node to allow for atrial to just pause that beat for a second before it passes it on to our Purkinje fibers. Okay, so we want to know how long it's holding it there. If it's holding it for too long, then we're looking at our heart blocks. Okay, so that's why we evaluate that PR interval. Okay. Okay, so the 5-step method to EKG interpretation. Now write this down. The first thing we're going to evaluate is our heart rate. We're going to evaluate our P waves. We're going to evaluate our P to QRS ratio. We're going to evaluate our QRS. And we're going to evaluate our PR interval. So evaluating those 5 things is going to allow us to determine, first of all, is this a normal EKG? And second of all, what type of arrhythmia is this that we're looking at? Okay, so we're going to, every EKG that we see, the first thing we're going to do is evaluate our rate. Okay, and we'll go into how to evaluate rate later. The second thing we're going to look at is our P waves. Then we're going to evaluate our P to QRS ratio. We're going to evaluate our QRS complex. And we're going to then evaluate our PR interval. Okay, evaluating those 5 things is going to give us exactly what we're looking at. So our rate, normal rate, is going to be 60 to 100 beats per minute. And we already talked about what we might be looking at with our heart rate. So normal rate 60 to 100 beats per minute. Anything below or above that is an abnormal EKG. Second of all, we're going to look at our P waves. We want to determine, are they present? Are there P waves, first of all? Are they upright? And are they smooth? Okay, so are they smooth like this? Or are they pointed? Or do they go down, or are they completely absent? So we want to say, do we have P waves? Are they upright, and are they smooth? Second, we're going to look at our P to QRS ratio. So for every P wave, do we have a QRS? Okay. If we don't have, so this is our atrial depolarization. If we aren't getting a ventricular depolarization with every atrial depolarization, then we have a problem. And next we're going to look at our QRS. Do we have QRS complexes? And are they less than 0.12 seconds? So are they about 1.5 to 3 small boxes? Okay, so here's our QRS. Is this area here 1.5 to 3 small boxes? If it's wider than that, then there's an issue, okay? And we'll need to investigate that further to determine what that may be. And then last of all, 5th thing we're going to evaluate is our PR interval. Now remember, our PR interval starts at the beginning of the P wave to the beginning of the R wave. So this is our PR interval. And what that's going to tell us is the onset of atrial depolarization to the onset of ventricular depolarization, essentially what's going on in the AV node. How long is that impulse being held? Okay, so how do we determine rate? So every EKG strip is going to be divided into large boxes, and within each large box there's going to be small boxes. So each large box represents 0.2 seconds. Okay, and each small box is going to represent 0.04 seconds. Okay, so we can just count these small boxes between our QRS. Remember, in every QRS should be a max, there should be about 1.5 to 3 small boxes, okay? So we can evaluate our QRS based on these facts. So large box is 0.2 seconds, the small box is 0.04 seconds, okay? So P wave, what are we looking at? We're looking for it to be upright. We're looking for it to be smooth. And we're looking that it's coming before the QRS. Okay, so these are our normal P waves. For each QRS, upright and smooth. our P to QRS. So do we have a P before each QRS? P wave, QRS, P wave, QRS, P wave, QRS. That's good. And then we're going to look at our QRS. We're going to make sure that it's 1.5 to 3 small boxes. So here's the start of it. 1 small box, 2 small boxes. So about 1.5 to 2. Okay, so that's about 1.5, 2 small boxes there. So that is going to be a normal QRS complex, as long as it's between 1.5 to 3 small boxes. That's going to be a normal QRS. Okay. PR interval. So our PR interval is going to represent the onset of atrial depolarization to the onset of ventricular depolarization. Okay, so what we want our PR interval to be, we want it to be 3 to 5 small boxes. So onset of P wave to beginning of the R wave, about right there. Okay, so we want to count how many small boxes between there. 1, 2, 3, 4. About 4.5 or 5. So that's just on the edge of a long PR interval. But we want it to be between 3 to 5 small boxes. Okay, and that one just fits within that criteria. 1, 2, 3, 4.5, 5. Okay, so those are the 5 things that we're going to evaluate. And we talked about what everything means, so we're looking at our P, we're looking at our QRS, we're looking at our PR interval, and we're looking at our P to QRS ratio. Those are the things we're looking at. We're looking at rate, first of all. We're looking at QRS. We're looking at P wave. We're looking at P to QRS. And we're looking at our PR interval. Okay? So those are the 5 things that we're looking at. Rate, 60 to 100. QRS, are they present? Are they 1.5 to 3 small boxes? P wave, present, upright, smooth. P to QRS, we want it to be 1 P for every QRS. And our PR interval, we want them to be 3 to 5 small boxes. Okay? So let's start. Here's an example here. So what's our rate? So there's a couple ways to determine rate. If you are looking at a 6-second strip, if you're looking at a 6-second strip, you just count the number of, you can either count the number of P waves, or you can count the number of R QRS complexes, and that will give you your rate if you multiply that by 10. If it's a 6-second strip, you count waves times 10. If it's not, or to be more precise, you can take, you count the number of large boxes between your R waves or your P waves, and you divide 300 by that. Okay, so we'll use that method. So let's count our number of R's. So here's 2 R waves, and let's count the number of large boxes between those. So here's 1 large box, 2 large box, 3, 4, 5, about 6. About 6 large boxes. So we're going to take 300 divided by 6. That's going to give us a heart rate of about 50 beats per minute. So we've determined our heart rate. It's about 50. So we already know that's abnormal. Okay, that's below 60, so it's abnormal. Next we're going to look at our P waves. Do we have P waves? Here's a P wave. Here's a P wave. Here's a P wave. So we have P waves. They're upright and they are smooth. So P waves are normal. And next let's look at our P to QRS ratio. So here's P wave, QRS follows it, P wave, QRS follows it, P wave, QRS follows it. So P to QRS ratio is normal. Next we're going to look at our QRS. We're going to say, do we have QRSs? Yes. Okay. And then we're going to say, is it between 1.5 and 3 small boxes. So QRS. Okay. So it's 2 small boxes. Let's check this one. QRS. Okay, about 2. QRS. About 2. So it's less than 3. So that's correct. That's what we want. And next we're going to look at our PR interval. For our PR interval, we want it to be between 3 to 5. So we'll take the beginning of our P, 1, 2, 3, 4, 5. So that's 5. PR interval equals 5 small boxes. So that's correct. We'll do it again. P, 1, 2, 3, 4, 5. So about 5 small boxes again. So everything is normal on this EKG here, except that our rate is a little bit slow. So other than our rate, everything is normal. So we can determine from this that this heart or this rhythm is in fact sinus bradycardia. Okay? Let's do one more example. So what's our rate? All right, let's look at our ventricular rate and let's look at our atrial rate on this one. So between the ventricles, we're looking at about 1, 2, 3, about maybe 4, 4 or so large boxes between each R wave. So we're looking at a ventricular rate of about 75 beats per minute. And we can look at our atrial rate. We have about 1, 2, 3, 4, 5 or so. So okay, so our atrial rate is obviously much. Okay, let's look between. So we have about one small box or one large box between each P wave. So our atrial rate is about 300 beats per minute. Okay, so there's our rate. So a ventricular rate is about 75 beats per minute. Our atrial rate's about 300 beats per minute. Okay, do we have P waves? All right, do we have P waves? Yes, we do have P waves. Okay. Are they smooth? Are they upright? They're not smooth at all. They're very jagged. They're very sawtooth. So they look like a sawtooth here, our P waves. So our P waves are not normal. Our P to QRS, do we have 1 P for every QRS? So is it 1 to 1? No, it's about 4 to 1. So that's abnormal. QRS, okay, for our QRS, we're going to look at, do we have QRS? Yes. Is it 1.5 to 3 small boxes between each? QRS, about 1.5. QRS, about 1.5. So our QRS are normal. So that's going to say that our ventricles are depolarizing out appropriately. So let's look at our PR interval. We can't really determine our P to R interval because we don't have the 1-to-1 ratio that we need. So our rate, about 300. We got P waves are sawtooth. Whoops. And our P to QRS about 4 to 1 or so. So this is an abnormal EKG, and we can tell that the problem is coming from our atria, right? Because our ventricles, our QRS is normal. That tells us that our ventricles are working appropriately. However, something's going on in our atria. We're getting a lot of firing going on from a lot of different places within our atria, although they are depolarizing because we're getting these defined waves here. So this rhythm is actually called atrial flutter, and because of those sawtooth waves, sawtooth P waves, we can determine that. So we have our heart here. Now our QRS, our QRS look normal, right? So we had our normal QRS. So that's telling us that our ventricles are fine. Ventricles are firing appropriately, and the rhythm is traveling right there. But we had the sawtooth P waves. So what that's telling us is that there's a lot of places within the atria that are firing, and that's giving us this multiple atrial firings going there for each ventricular firing. So you're getting all these firings here, but our AV node is actually filtering those waves, and it's only sending one down, okay, at an appropriate rate from our AV node, but we're getting all these atrial firings from many different areas. Okay, so that's atrial flutter. All right, last one here. So let's look at our rate. So we have about 1, 2, 3, 4, maybe 5 or so. Our rate here is going to be about 55. Okay, maybe 5.5, maybe 5.5 or so. Large boxes between each R wave. Okay, do we have P waves? Let's check. P wave, P wave, P wave. Okay, we have P waves. Are they upright? They're going in the upright direction, and they are smooth. Okay, so P waves look good. QRS, or P to QRS. Here's P wave before QRS, P wave before QRS, P wave before QRS. That's correct. Let's look at our QRS complexes. Okay, so our QRS complexes are present. Are they 1.5? Okay, about 1.5 there, about 1.5 there. Are they 1.5 to 3 small boxes? Yes. So our QRS is our normal. Let's look at our PR interval. So what we want to determine with our PR interval is it between 3 to 5 small boxes. Okay, so here's our R wave right there. Here's the onset of our P. So 1, 2, 3, 4, 5, 6.5. 1, 2, 3, 4, 5, 6.5. So our PR interval is long. It's greater than 3, or it's greater than 5 small boxes. So what that's telling us is that here's our heart. So our SA node is firing. It's sending our impulse down here to our AV node, but for whatever reason, we're having a hold up here. So it's kind of holding this a little bit too long, but yeah, it is in fact firing, sending that down to our Purkinje fibers. So for every SA node impulse, we are getting a contraction through, or an impulse through our Purkinje fibers, but for whatever reason it's being held up here in our AV node. Okay, so that's what that's telling us. So our rate is a little bit slow. P waves are normal, P to QRS is normal, QRS is normal, PR interval is long. So this tells us that we actually have a first degree heart block, AV heart block. Okay, so first degree block in our atrioventricular node. Okay, so with your first degree AV block, all you're really going to see, you're going to see everything normal except your PR interval is going to be long. So that's why it's important to look at your PR interval. This isn't sinus brady because we are actually having a hold up here in our AV node as well. All right, so those are the basics of interpreting our EKGs here. So again, I just want to go over the 5 things that you want to always look at with every EKG is going to be your rate first, P waves, are they present, are they upright, are they smooth? QRS, is there, P to QRS, is there a 1-to-1 ratio of your P wave to your QRS? QRS, do you have QRS complexes? And are they 1.5 to 3 small boxes between them, between the Q and the S? And then a PR interval, do you have, what's the length of that PR interval? Can you determine it, first of all? And is it 3 to 5 small boxes? Okay, so that's what we wanted to go over today. That's just a basic introduction. Rate, P wave, P to QRS, QRS, and PR interval. Those are the things you want to look at with any EKG, and that will help you determine exactly what you're working with. All right, now with this, I want to offer you a free EKG worksheet that will outline all the basic rhythms you need to know and what's actually going on with these 5 criteria with each of those rhythms. If you go to nrsng.com/ekg-chart, you can get that free chart, and that'll help you determine and analyze all these rhythms that you need to look at. All right, that is it for now. I appreciate you watching.
Okay, so we are going to stop it there.
Good grammar and spelling.